this video, I'm going to show you my strongest proof for why the Earth is not a globe as the standard model describes it. One of the problems with helping people to understand that the globe model is not the right model for our world is that a lot of people accept the globe model and the standard theory that goes along with that without really fully understanding the details of it. And once you start looking into the details, taking into account the different aspects of the theory across the bigger picture, you start to see that it's failing. For me, it comes down to gravity. The standard model of gravity simply doesn't work. It doesn't work with the globe Earth. And so the theory is clearly wrong and must be rejected. And so the globe Earth model must also be rejected. So let's start with that. The theory of gravity has two branches. On the one branch, you have gravity at the quantum level, where you need particles to transmit the gravitational force. And these particles are called gravitons. Except we've never actually detected a graviton, despite billions of dollars having been spent on graviton detecting experiments and years of conducting these experiments. We have failed. Well, scientists have failed again and again and again and again and again and then again to detect any gravitons. This is a problem because in order to reconcile gravity at the macro level, the things that we see around us, with gravity at the quantum level, which you have to do if you're going to make a theory that explains gravity and doesn't just describe it but explains it, it has to account for gravitational effects on large objects as well as gravitational effects on small objects. One of the reasons science must do that is because science says that humans are not special and that we are here randomly and the Earth is here randomly and we have no special place and special role for that. So the idea that things that humans consider large in reference to us, that those things are governed by one rule of gravity, and then things that are small to human beings are ruled by a different set of gravity principles or mechanisms, that's problematic, because then you have to acknowledge that there's a reference frame that has to do with human scaling, that things that for humans are too small to see, there's one rule. And for things that are visible to humans, then there's a different rule. There's a different way that this force acts. So the theory of gravity doesn't work at the quantum level because it requires gravitons. And we have failed to detect gravitons. We're not able to detect gravitons. We haven't found them. And so we can't keep pretending that there are gravitons just because it fits the theory that we like and want to keep using. The fact that we can't find gravitons suggests that they don't exist and that the theory is wrong and the model is wrong. Now let's look at the problem of gravity at the other end of the scale. What we're told is that at very large scales, gravity actually warps the space-time fabric that our universe is embedded in. What is the space-time fabric? It's reality itself. It's reality around you. It's the field in which objects find themselves. And so things that have any density or mass, they make space-time bend around them. This was Einstein's theory, and everyone just kind of jumped on the bandwagon. The problem with this theory is that, well, it's a little bit hard to prove because obviously you cannot take a box of space-time, open it up and manipulate it and do tests on it. It's what we are in. It's not air, it's not space, it's space and time. It's the construct. So what we have in space-time are objects and then gravity wells around these objects. So the Earth has a gravity well, and the gravity well is basically the kind of indentation or the curvature of the space-time fabric of space that's caused by gravity. Here's another interesting thing about scientists' explanation of gravity. It's actually not an explanation, it's a description. And so they can describe what gravity does, but they're not really telling us how it works. And when scientists tell you something, I think it's very useful to look at, are they telling me what is happening, or are they telling me how and why it's happening? Because for a theory to explain gravity, I want to know why and how it's happening, not just what's happening. I know what's happening. Objects are falling. To tell me, well, objects are falling because space-time is curving and objects are following the curve of space-time, and then that makes them fall into the Earth. Well, that doesn't tell me very much about why space-time is curving, by what mechanism and how, what's causing the curvature of space-time. To say, well, gravity's causing it, well, that's circular. You're saying, what is gravity? It's curvature in space-time fabric. Well, what's causing? How does that happen? Oh, well, it happens because gravity. That's not an explanation. That's just a description. And science should be giving us explanations. We know from physics experiments, specifically experiments replicating the Wheeler's delayed choice thought experiment. Once upon a time, John Wheeler, this physicist, came up with a thought experiment. He called it the delayed choice experiment. And the reason, oh my goodness. This is why it's hard to make videos quickly, because there's so much backstory that we often need in order to understand the answers to simple questions. And I think that's why scientism has taken such a hold on the general population, because people don't have time for the backstory. They just want the simple answer. And there is no simple answer without complicated information that backs that up. And so if you're not willing to process the complicated information and you just want the simple answer, then you'll never learn how to assess the validity of that complicated information. And so then that complicated information could be wrong, and it could be leading to wrong simple conclusions. And you'll have no way of knowing that if all you're taking away from it is that simple conclusion that you can put in your pocket and confidently carry around with you. The Earth is a globe. Gravity because gravity. The Wheeler delayed choice experiment basically showed that photons are sent from a source. They go through, let's call it a maze, and then they're detected on the other end after they've gone through the maze. Here's the thing with the maze. It has different corridors, and there are gates in the corridors. And so you can leave one gate open and one gate closed. You can leave both gates closed, both gates open. Here's the important point. When you detect... Are those bugs? No. John Wheeler had a thought experiment that had to do with photons going around a galaxy far away. And so the photon is traveling through space as a wave because it's undetected by humans, and it goes around the galaxy as a wave. We set up an experiment here on Earth, and we can set it up in one of two ways. We can set it up to determine on which side of the galaxy that photon traveled as it went in around the gravity well that the galaxy creates. And there's this effect called gravitational lensing, where large galaxies will bend light, and so the light actually goes around both sides of the galaxy. And so sometimes we get a bit of a halo effect, or we get duplicate images because the light is coming around both sides. And so then you get the image here and here that's come around the galaxy, rather than just the one image. What's important is if you set up the experiment to detect which side of the galaxy the photons are traveling, then the photons travel through space as particles, and they either go around the galaxy on the one side or they go around the galaxy on the other side. When they arrive at your detector, they arrive as particles, and you can see on which side they went. If you set up your experiment to not detect which side of the galaxy the photons came around, and you only look at where they arrive on your detector, then suddenly you get an interference pattern, which shows that the photons actually traveled as a wave around the galaxy, and that wave interfered with itself, and so you get an interference pattern on your detector. So as soon as you look to see which side of the galaxy the light is coming from, then the light acts as a particle and only comes from one side or from the other side. But if you don't look at which side it's coming from, and you only look at your detector results, you get an interference pattern from light that's traveled as a wave around the galaxy. But here's the problem with that. The light traveled around that galaxy millions of years ago, because the galaxy is millions of light years away, which means that it takes millions of years for the light to travel through empty space all the way to your detector. And so the experimental setup that you choose today affects what the photon did millions of years ago. So in the late 90s, a number of physicists were actually able to test this thought experiment in reality. And they set up systems with beam splitters and gate systems, and the details aren't important right now. And if you do want to know about them, I'll put some links down below for articles that you can kind of look up. Or you can just look up delayed choice experiment or quantum eraser. You'll find some results in that. Or go to your public library and look up the Scientific Americans from the late 90s, and you'll get some nice glossy articles in that magazine that cover this topic. In some ways better than what you can find on Google. The experiments that use the beam splitters, basically the photon goes down two paths, and there are gates along the path. And so if you set it up so that you're only looking at the photons when they arrive, what you find is that the photons will travel as a wave, and they'll go through both paths, and then you'll get an interference pattern on your detector. But if you look to see which path the photon is taking, or if you look to watch the photon as it travels down both paths as a wave, what happens is then it doesn't travel as a wave, then it collapses into a particle, and it travels through either one or the other path, but never both, because there's only one photon. And so then in that situation on your detector, you find a particle collision pattern, and you can see whether the photon went through the one path or through the other path. But here's the interesting thing. When they close the gates that are along the pathway, what happens is that they close the gate after the photon will have traveled through that area of the path. And so the photon travels through that area of the path, and then after it would have been past that point, then one of the gates is closed and you detect the light. By closing one of the gates, that gives you information about which path the photon would have traveled on. Either it travels on the path where the gate was left open, or it traveled on the path where the gate was closed. If it was on the path where the gate was closed, it won't reach your detector. If it travels along the path where the gate was open, obviously it will reach your detector. So by having the gates there, you can determine, you're watching which path the photon is actually taking. That forces the photon into a particle rather than leaving it as a probability wave and finding your interference pattern. Here's where it gets mysterious. They run the experiment, but they close the gate after the photon should technically have traverse that area of the path. And what they find is that regardless of when they're closing the gate, they're still getting the effect from the photons that reflect whether the gates were open or closed. So if they close the gate on path 1, after the photon is well past the gate section of the path, the photon seems to know that the gate behind it has been closed, which forces it into a particle, because now you have information about which path that photon was traveling along. And so the information of the gate closing behind the photon forces the photon into a particle, and that's what you detect. And if you don't close the gate after the photon has traversed through that area of the pathway, then the photon responds to the fact that you won't have information about which path it took. And so then it takes both paths as a probability wave, and there's an interference pattern. And so what does that tell us that's relevant here? What this tells us is that the photons, when they're detected, measured, observed, they take current information into account. The photon responds to the closing of the gate, even though the gate closes after the photon has already gone down that pathway. So the photon isn't responding in the moment of the gate closing because the gate closed in the past. The photon is responding with information available to it in the moment of detection, not to the information as it was in the past. In the past, both gates were open, and so the photon should have been traveling as a wave. But after it passed the gates, we closed one gate. So now we've changed the current reality. Now, information within the system would be able to tell us which path the photons are taking. And so then the photons collapse into particles. Okay, so how does this relate to the globe Earth theory being completely wrong? Here's our Earth. Can you see that? Can you see it? I feel like Grace Helbig.
Can't see it, can't see it, can't see it. This.
You probably don't know who Grace Helbig is. Okay, so, I'm gonna have to do a diagram. I keep wanting to use my whiteboard, but then it's not on my wall anymore, and so it's hard for you to see it, and I have to angle it, and it's hard for me to hold. But I might try moving around.
From above the North Pole, the equator spins counterclockwise at about 1670 kilometers per hour. Relative to the sun, Earth orbits counterclockwise at 108,000 kilometers per hour, along a path tilted 23.4 degrees to its spin. Within our local neighborhood of stars, our entire solar system is drifting 70,000 kilometers per hour, roughly in the direction of the bright star Vega in the constellation of Lyra. And our solar system is part of a giant galaxy called the Milky Way. On a plane tilted about 60 degrees, approximately like the windshield of a car, looking from above Earth's North Pole, our entire solar system races clockwise around the galactic center at about 792,000 kilometers per hour. Our whole galaxy is also moving through the universe.
Here we have the Earth, and the standard globe Earth model tells us that the Earth is rushing through space as it orbits the sun, and with the sun through the galactic disk, and with the galaxy towards the great attractor. And so in every moment, the Earth is rushing around at very high speeds in different directions. And so we're only going to look at one direction right now. We're going to look at the Earth as it moves around the sun, according to the standard globe Earth model. So the Earth is here at time 1, and at time 2, the Earth will have moved and we'll find it over here. What's important here is that this is time 1, and 8 minutes later, this is time 2. So in the course of those 8 minutes, the Earth, traveling at 66,000 miles per hour around the sun, has traveled this huge distance. The standard model also tells us that around the Earth, there's this huge gravity well because of the Earth's gravity, because of its density and its mass. And the moon orbits the Earth in large part because of the gravity well around the Earth. And so the moon is constantly falling in towards the Earth along the gravity well. So what happens with our photon? Our photon leaves the sun when the Earth is here at time 1. 8 minutes later, the Earth has moved to position 2 at time 2. In those 8 minutes, as the Earth travels, the gravity well around the Earth obviously travels with it, because the Earth is the cause of its gravity well, is what we're told in the standard theory. And so the photon that left the sun 8 minutes ago is on its path towards the Earth, but it's being warped. Its path is bent or curved because space-time itself is curved. Here's the problem. The photon is moving with this curvature. That's the curvature it's taking into account when it leaves the sun. But when it arrives, the Earth is up here, and the curvature of space-time has changed. It's moved over here. Now, here's the crux of the problem. Photons, as was proved with the delayed choice experiments, take current information into account, which means that when a photon is detected by you, when it hits your eye and you see something, you see the blue sky, that's the moment in which that photon collapses from a probability wave into a particle and is detected by you. And that's the moment in which the past history, which is the path history of the photon, is created. But the photon takes current information into account. And so the photon necessarily would have to take the curvature of space-time as it is in the moment you detect it into account as it creates its past history. Because that's the only information that's available to it in that moment. Because the photon doesn't have enough information in that one snapshot of time, in that one moment, to guess at the trajectory that the Earth is on. The photon doesn't know if the Earth is moving from over here to over here. And it also doesn't know if the Earth is moving this way, but also left to right as our entire solar system swings towards the great attractor. It also doesn't know that the Earth and the Sun are also rising up as we move toward the galactic disk, or actually since 2012, roughly, away from the galactic disk. In order to calculate the trajectory of the Earth across all these different movements, a photon would need to be able to see a pattern. And in order to see a pattern, you need information at different points in time to see a pattern in movement trajectory. So the photon doesn't have information about the Earth's trajectory because it doesn't have the ability to see the pattern of movement over time. The photon only has the information that's available in the present moment of detection. And so, if the photon is here when it's detected, then it will take into account the space-time curvature that we find here around the Earth. And the path created will have to be in accordance with the space-time curvature around the Earth here at time 2. The problem with that, of course, is that if we follow the curvature at time 2, it won't lead us back to the sun. It won't lead us back to where the sun was 8 minutes ago. Because the sun also has an enormous gravity well, and the sun is also moving over those 8 minutes. And so the gravity well of the sun itself has shifted and changed. And so the photon that's creating its past history of where it traveled through space only has the information at time 2 to recreate its trajectory. So it has to take the space-time curvature as it exists at time 2 to plot its past history, to plot its path history. And so it cannot create a path history for a sun and earth and space-time curvature as they were 8 minutes ago. Because it has no way of formulating that information from the information available in the moment of detection. Do you see? To me, this is very clear and very obvious, but it's come to my attention that this is less clear and less obvious for others. And so I don't know what it is that I see clearly that some of you won't see clearly, and some of you will see clearly. The people that maybe think like I do, you'll get this right away. But for some of you who think differently, this will be harder, and I don't know how to simplify it, or I don't know how to express it differently. It's not just about simplifying it, because I think it's more that people think differently, visually or conceptually, abstractly. And so it's not about simplifying it for people, but it is about presenting it in a way that makes sense to them. And I'm not sure that I'm doing that. And so please let me know in the comments, because if you can help me figure out how to communicate these ideas in ways that make more sense to more other people, then I can make better videos, and that's more fun for both of us. So the point here is that if in the delayed choice experiment, the photon takes into account the information in the moment of detection. So in the moment of detection, it looks to see, were you observing which path I was taking? And if you were, then I'm going to let you see me as a particle. But if you weren't, then I'm going to leave myself as a probability wave, and there's an interference pattern. In this instance, the photon is traveling as a probability wave if you're not looking at its path through the curvature of space-time on its way to the Earth. But as soon as you detect the photon and you look and you see where it's coming from, if we set up an experiment here at time 2 and we look at the photon as it arrives, then we'll get an interference pattern of all the possible paths it could have gone through. But if we look to see which path it took of all possible paths, right? Let's say we look at which side of the ISS orbiting in space, if we were to say around which side of the ISS did this photon travel, then that would force the photon into a particle state. Once you force it into a particle state, then it can't have traveled as a probability wave across the entire universe. It will have necessarily traveled as a particle from the sun to your detector. But when it creates that past history, not only will it choose one side or the other of the ISS to travel around, but it will make its choice based on the information it has in the moment you detect it or measure it or observe it. So as soon as you detect it, it takes the information available to it in that moment, wherein the Earth is over here and the curvature is such and the sun is here and its curvature of the space-time around it is such. And the problem with that is that it takes the photon 8 minutes to travel from the source, the sun, to you, the detector. And in those 8 minutes, the gravity wells have moved. The space-time curvature has changed. Gravity wells aren't just relevant to the Earth and Sun locked in orbit, moving together. The moon is doing its own little thing running around the Earth. And so that movement of the moon would distort the gravity well of the Earth as it affects the space-time fabric around it itself with its own gravity well. And so there's something called the three-body problem, which is something we won't go into. You can Google it if you are interested. It's relevant to this in terms of the complexity that it adds to the problem. Basically, what it comes down to is the photon leaves the sun 8 minutes in the past, but it only takes information into account 8 minutes later when it's detected. And in those 8 minutes, the gravity wells around the Earth and the sun have changed, not only because the position of the Earth relative to the sun is different, but also because the position of the moon is different and the position of Mars is different. So all these other bodies that are also distorting space-time curvature around them, that's all changed in those 8 minutes. But the photon has no way of reconstructing the earlier curvature because it has no way of figuring out what is moving in which directions. It only has the information available to it at time 2 when it's detected. And so because of that, the photon would never be able to leave the sun at the point of origin at time 1. It would only ever retrace a path leading to the sun where it is at time 2, but the sun isn't at the location of time 2 at time 1. So the photon would never be able to trace its path back to the sun. Do you see? And so this, in and of itself, completely disproves the entire Einsteinian view of gravity, space-time curvature, and it disproves the globe Earth rushing madly through space. The entire theory, the entire standard model falls apart when you apply information that we find in one, maybe more esoteric area of physics, and we take it back to the main domain that maybe more people are familiar with. And that's the problem with science today, is that these little bits of new information that are being found on the fringes that destroy some of the fundamental elements of our standard models are acknowledged, but they're not really taken into account, in that the standard models aren't being rejected when they really should be. The theories that are disproven aren't being rejected when they necessarily must be. You cannot accept the results of delayed choice experiments with particles and accept the standard model of gravity and the Earth and the sun and what's happening between them and how fast they're moving, the fact that they're moving at all. You can't reconcile these different pieces of information. And so what do we do with this? Well, one of them, the gravity, space-time curvature, that's just a theory. We don't actually have strong experimental evidence that proves that to be true. Whereas the delayed choice experiment has been done and replicated, and it has been shown to be true experimentally. We have evidence, we have reproducible evidence that the delayed choice experiment leads to the outcome, the same outcome when you replicate the experiment. The photon takes current information into account when it's detected, and it creates its path history. That's experimental evidence. That's data. You can't just wish that away. You have to incorporate that into your model. And if you can't incorporate that into your model, which we've seen clearly here, you cannot, then you have to reject your model because your model is wrong. It doesn't fit the reality that we observe. It doesn't fit the outcome of our experiments. It's the wrong model. It's a bad model. It's the wrong theory. It doesn't work. You have to reject it. The results of the experiment on the delayed choice can't be rejected because they've been replicated and they've been tested, retested. The experiment's been run by different groups, by different people, but using different equipment in slightly different formats. And so we know that those results are sound. We know that the problem with this discrepancy doesn't lie in the delayed choice, photons creating their past in the moment of detection. So then we must conclude that the problem lies with the unproven theory of space-time curvature causing gravity, of the Earth and the Sun rushing madly through space, of photons leaving the Sun, traveling, bending around space-time curvature. As we're told, light bends due to gravity. That whole theory is disproven, was disproven in the late 90s. It's 30 years later, and physicists have still, to this day, failed to talk about this with the public. Why doesn't the public know? This is important. And nobody knows. Now you know, and I know, so we know. So let's talk about this. And to me, this is the most convincing proof that the Standard Model is wrong and must be rejected. #flatter. Good night. Thank you again to my kind commenter for putting the time in to posing a thoughtful question. We had a bit of a dialogue back and forth, and it was really nice. It was satisfying. It was challenging in an interesting, polite way, and that was wonderful. And so I hope that this video response gives you something to think about, and hopefully you'll come back with comments or questions, or I don't know, maybe your mind is blown now and you're just going to go into shock for a few weeks. That's okay. Do come back, and we here in the Flat Earth YouTube community will welcome you with open arms. Good night.